So I'll just really quickly say I think I owe everybody an apology here. Don't know why I've been so ill-prepared or unable to read an agenda, but I have made a mistake and juxtaposed two topics. One was a 5-minute lightning round topic, which my understanding was object serialization is what I did that for, but that was supposed to be this 20-minute deep dive, and I prepared things differently. So this was supposed to have been a lightning round topic, and I'm going into it in quite a bit of detail. So I apologize to everybody for that change in topics. I had not intended to do that. It's my fault in the way I was reading things. So I'm going to talk about advanced concepts and issues with the H5Z-ZFP compression filter. Just a real outline here. I'll talk a little bit about the compression library, the ZFP compression library, and then just a sort of grab bag of topics on how the compression filter that uses ZFP works, endianness portability, handling data sets that are greater than 4 dimensions, even though the ZFP library has a max of 4 dimensions that it supports, understanding the interplay between the ZFP library's chunklets and HDF5's chunks, partial writes and ZFP chunklets, other things having to do with ZFP chunklets, and then reading and writing ZFP compressed arrays, and then finally letting ZFP compression parameters vary over a single data set. So I'll just go into these real quickly. You can find the H5Z-ZFP filter on GitHub, it's based on the ZFP library. That library is developed, or its development is led by Peter Lindstrom. There have been many developers that have contributed to it, but it's led by Peter. It supports lossy and mostly lossless compression on 1, 2, 3, and 4-dimensional data. And integer and floating point data as well. And it supports 5 modes: a rate mode, which it guarantees a fixed bit rate. A accuracy mode, guaranteed certain accuracy. I think that's let's see, relative error bounds, and then a precision mode, just a kind of sort of absolute error bounds. There's an expert mode with it, and there's a reversible mode. That's the lossless mode of ZFP, and it's mostly lossless. There are cases where it can lose a little bit. It can run on GPUs and even OpenMP kernels, although that's not been integrated with the H5Z-ZFP compression filter yet. And it creates a data stream that's endian agnostic, which takes me to my first deep dive topic. So how do we deal with endianness portability? The HDF5 library provides data that's endian portable. You can write on a big endian machine and read on a little endian machine transparently. But the ZFP library operates in an endian agnostic way. So when you uncompress data with ZFP, you get the correct endian result in memory when you do this. But the problem is HDF5 is not expecting that to happen. It's expecting to what's be produced on the reader to be what was originally produced by the writer at that point. So if you're on a different endian machine, you've now created the correct endian, but you've now got to byte swap that so that when HDF sees it, it's byte swapped it back into the correct order. So there's actually logic in the plugin that does this. In addition, we don't allow endian targeting. So for example, if you were running on and I forget this, somebody remind me if I get it wrong. I think big endian is almost gone now. Is that correct? Almost everything's little endian. But if you're running on a big endian machine and don't expect a lot of your workflow to be doing that, you would, in theory, you'd want to say, well, I want to target on write little endian. I want it to be little endian. That way, all the other consumers in your workflow aren't constantly byte swapping every time you're reading. Can't do that with this filter because of this problem. And this is a little bit of the code that's in the filter there that actually handles the byte swapping, basically ruining a correct result already so that HDF5 can unruin it when it gets it. And it only happens in certain contexts. So handling greater than 4D data, the ZFP library has a max of 4 dimensions that it operates on. So how do you handle data sets that have more than 4 dimensions with the ZFP compression filter? You can do that. All you need to do is ensure that at most only 4 dimensions of the chunk are non-unity. So if you have a 6-dimensional data set, the chunks that you define, 4 of the dimensions can be above 1, but the remaining 2 dimensions have to be 1. And as long as that's the case, the ZFP filter will only see things that are 4-dimensional or less if you made some of the other dimensions unity. So yeah, the magic of that is that HDF is basically then just delivering to the filter data that looks 4-dimensional or less. When you have a choice over which dimensions you're going to set to Unity, you want to choose the dimensions that are the noisiness effect. You want the dimensions that ZFP compress well are those that are the smoothest. So you would want to pick, if you have some understanding of your data, the dimensions of the chunk that you want to be non-Unity are those that are the smoothest in your data. So that's just another deep dive. So ZFP chunklets, the way that ZFP works, it operates on quanta of chunks 4 to the D chunk. So it basically quantizes it so that the chunks, let me make sure I say this right. Everything has to be a multiple of 4 in every dimension for ZFP to operate effectively. And if it's not a multiple of 4, that's fine. ZFP internally will pad things to do its work. So if you've got a chunk that's say 27 by 101, ZFP is actually going to treat that by 28 by 104 ultimately underneath the cover. So that's about a 6.4% waste, not too bad. But imagine if you've got a 3D array and you're sort of handling it slice by slice. So you got 1024 by 1024 by 1 or by 2 in memory. That's a 50% waste because there's the two extra dimensions, or the 2 steps in that extra third dimension there are essentially not being used. So you want to be aware of this when you're using H5Z-ZFP and the interplay between ZFP chunklets and HDF5 chunks. So a third thing, I will get back to that last bullet on dealing with data in 3 dimensions and slices and so forth. So partial writes in ZFP chunks. So as we've talked about many times already today, chunk size and shape in relations to partial writes and reads impact performance quite a bit. So imagine a case where you've got a data set that you're going to write and you're doing partial I/O on the data set. So in scenario 1, you have I/O requests where the chunks that you're writing to the file partially overlap with chunks that have already been written to the file. Then in that case with HDF5, and correct me if I'm wrong, but I recall exchanging email with you about this, Dana, maybe as much as a year ago, but HDF5 will have to basically engage in a read, modify, write scenario for those partially overlapped chunks. I'm going to pause if somebody hugely objects to that. Understand. Neil, there is, okay. Okay. Didn't know that. What's the name of that option? Okay. All right. So Neil has shared that there's a property, and now there's 201 knobs. Whoever said there, I think it was, all right, there's 201 knobs. So there's a property down there that potentially can control this and mitigate this problem. So, so thank you. So write scenario 2, your I/O requests might partially overlap, but there's no chunks already written to the file. Well, HDF5 is going to treat those essentially in fill value mode already. And the problem with that is the fill value may interfere with the compression filter's ability to deal with those chunks. So you probably want to either select a fill value that actually matches what the ZFP library would want you to use. But, well, wait a minute. That's actually not possible because ZFP does that on a chunklet by chunklet basis to decide what it thinks the right fill value is. So nix that. You can't do it. Just understand it's a problem. It'll interfere with ZFP's ability to do a maximally high compression ratio. It'll basically reduce the compression ratio. Okay, another thing to understand about these ZFP chunklets is imagine you're in a scenario where you're at the outer loop of your simulation code and you're writing, say, maybe a slice, 2D slices to a 3D data set over time. So you've got this massive compute loop, you finish it, you write another slice out to the file, and you're sort of iterating over time. Well, in that case, if you want to avoid some issues with performance, you're now required to buffer up in memory 4 slices so that you meet ZFP's chunklet requirements before you do that write. And depending on how, if this is a big time iteration, depending on how much memory that is, that could potentially be a problem for you to buffer up 4 time steps before you actually dump them to the data set. But it is an issue if you want to avoid some of the issues with ZFP chunklets. Okay, ZFP compressed arrays. In this case, what you have in memory is an actual compressed array. And those usually work In fact, I think they only work with ZFP library's rate mode of compression. So the array can be randomly accessed in memory. All the little, it basically needs to achieve a fixed size for the compressed pieces of that array. And the only way you can do that is in ZFP's rate mode. But bottom line, if you've got compressed data on disk, you don't want to have to read it into memory, uncompressing it, and then recompress it in memory so you can have a compressed array. You want to read the compressed data from file into memory without it being uncompressed. So same thing, if you've got it in memory, you want to write it to file, you want it compressed in the file. If you've got it compressed in memory, you don't want to have to sort of like, well, let me uncompress that first so I can give it to HDF5 so it can compress it and put it in the file. And the long story short there is you have to use the read and write chunk methods to do that. I really wish it was possible, because this is new code now, it's a different logic path I need in, consumer and producer. I just wish there was a way to add yet a 202nd property in the file so that it would just bypass the filter. It would know to bypass the filter under these conditions. So let's see. And I believe this is, okay, so another thing about the ZFP, H5Z-ZFP filter is it captures the ZFP library compression parameters in the CD values for the filter. These are essentially this array of unsigned ints that's sort of high-level metadata that basically controls the filter in HDF5. And it goes into, I think that goes into the dataset object header or something down in the HDF5 library. So that's good because now you don't have to store those parameters for every chunk. But the truth of the matter is, if your chunks are big, and they ought to be big if you want to get good performance, good I/O performance, you could have the ZFP compression parameters vary from chunk to chunk to chunk and just store, I think it's 64 bits of ZFP metadata ahead of each chunk in the file. We haven't done this yet, but it's something we want to look at in the future for the way that this filter works. And again, for reasonably sized chunks, that additional ZFP metadata in each chunk is completely negligible. I think that's my last slide. Yeah. So I'll end there and answer questions if there are any or comments. Yeah, Mark.
So with what you just said, the story is what they sound chunk itself. The one issue I think is that chunk because if it gets corrupted, then
good point. Maybe, yeah, I'm not sure what to do about that. Good point, though. Although, I think if you, I think if you know you need to check some of the data for any reason, something else is probably driving the need to check some other than that one loss of that little bit of metadata there. So I'm not articulating this quite right, but if that's important to you, you probably need checksuming for other reasons of what I'm saying. Yeah, no, I mean, it would be better to write many chunks at once, for sure.
Right.
Yeah.
So that's why I'm trying to wonder if the right version of five chunks there.
So
you can use it for compressed chunks for reasons.
Yeah.
Yeah.
I think for chunks kind of also talk about
And when you say multi-threaded compression, it's like multiple threads working on one chunk or threads working on each chunk?
So for people online, if you didn't hear that, the questions have to do with the read chunk and write chunk and the iterative versions of those, and whether or not there's some optimizations that could be used to handle many chunks at once. And I do think that that's a relevant potential issue.
Right, and computer. If you have several chunks that like an application, maybe they have the size of node, so they will provide the keys to our input chunk. We probably do the allocated depends on the second order, right? And people be allocated space that threads can provide particular chunks. With no sizes and addresses. Just because it's bold. But even exposing allocation from the library when we create and then index of that data, the more like the space right? That's what they know that they never did that. And if it's exposed to API to application, they can do it. They can do it.
We're using
Library, because users provide all information about compressed chunks.
Okay, so there's been a little bit deeper dive on this topic. The one thing I want to make sure that everybody understands, and when I present before I turn it over to Alex, is all the things that I pointed out are potential gotchas. Are not gotchas where things break. They're just gotchas that reduce your compression performance, either time or space of your compression performance. So they are things you need to pay attention to. So okay, Alex, are you? Oh, all right. Thank you.